So for our next speaker is Daehyung Park, an assistant professor at KAIST. He has a very impressive body of work in multimodal robotics, particularly in manipulation and planning. And he has some really cool stuff on how to semantically ground them in language. So I think this will be a good, interesting perspective. So please, whenever you're ready. Yeah, found me spot.
So hello everyone. Is it work? Yeah. I turned off, so it must fine. So okay. Thank you for introduction. I'm Daehyung from KAIST, and today I'd like to talk about our current work, that is the development of the robotic companion from natural language grounding to the safe execution. But here I will a little bit more focus on the language grounding. Oh my God. 1 second. So throughout my PhD, I and my colleagues and also my students were some mentors. We have tried to develop some various robotic assistants to help people with disabilities or some the elderly to enable them to perform some independent tasks, some for activities or daily living. So we have developed some robotic assistive feeding and also wearing and also various some teleoperation device for them. So the technologies not only include the perception or manipulation skill learning, and also we try to provide some web browser-based teleoperation services and also some gesture-based one. Actually, where we didn't use any language part, that is because the people couldn't speak. So anyway, so this kind of technologies are not only important for the some house domain, it can also be very used for the military domains too. Instead of sending soldiers to the dangerous environment, instead if we send some robot and then remove some bombs or some obstacles, we will be very we will be able to reduce some potential exposure of the soldier in dangerous environment. So here the point, what I want to say is the two applications are different, but the inherent necessary technology are very, very same. So robot understand our command and then perform some complex task for us or with us. So we call this kind of robot as robotic companion or teammate. So now our natural question can be what we have to develop, what kind of thing we have to work on. So to know that, we have to investigate the meaning of the terminology. So I just asked ChatGPT, what is that? What is the robotic companion? He say it's the some intelligence, some unit that can communicate with us through some conversation. And also if we ask what that is the robotic teammate is, it say it's some unit that directly or indirectly doing some task for us with some technical or physical skill. So something that we need to develop is make some robot understand our intention and also task execution capabilities. So, but here everybody know it's hard. It's always hard to develop any individual component for the robot. So that is why most of the current robots still in the cage and then doing some repeated job, even though there is some small variation. And also there can be also some robot in the some human environment. We say there is some coexistence system, but still we cannot see some really collaborative robot that can tightly collaborate with us through some interaction. So how can we develop a really collaborative companion robot? So I and always my friend, colleagues, and the students are thinking about some new intelligent architecture. So this is some conventional architecture that always we are thinking about, given a mobile manipulator. If you have some many sensors, so they observe the environment and then build some world model, and then task planner, and then low-level motion planner. Sometimes you're gonna have some finite definition machine, for example, some behavior tree. So they're monitoring and then asking to perform more complex tasks, following your some symbolic task plan. So if this is a robotic companion, it must able to understand our intention. To do that, here many people are working on natural language understanding or grounding. But as you may know, our instruction is not long. There is no time to prompt engineering. It's very short and ambiguous. So what that means is the robot, as like some human, it has some more equivalent level of some knowledge. So this includes common sense knowledge or some physics law, and also our human task is a really longer time horizon of task. So which means it also needs to know some various skill. So we call basically such kind of information as knowledge base, and our ultimate goal is finding necessary control output given our instruction and knowledge model and world model. So here, these colorful boxes are that I'm working on here. I will focus on natural language part today, and I will show some our recent work. So basically, we are working on some grounding thing, instance-based grounding, and also following some task planning. So as everyone knows, natural language grounding, there is some mapping process between our instruction and robot's knowledge that includes some knowledge about the instance in the world and what are some skill that it knows. So using the factor graph left side, we can represent its grounding process as some identification of the maximum correspondence between the two information, object instance or instruction. So, and using this maximum correspondence, robot, if we listen some command like some pick up the leftmost blue block, it can convert that command into some more interpretable language that robot can perform. So they're identifying object in the world and then associating with object, and then it can grasp something. So we strongly believe this kind of technology will going to be really helpful to automate some future factory. This is actually some demo of the flight wing assembly. It is really hard to automate it, but using this kind of language-based robotic assistant can collaborate with the operator. It will be able to expedite some assembly process. The sound is really weird. And also recently, the advance of the deep learning and also large language models show some great success in many application areas. For example, in unstructured environment without some massive data collection or some fine tuning, we are now able to see robotism driving in the unforeseen environment. And also thanks to this LLM like some model, some robots are now now making some complex task plan. It's not super complex though. And also, even this year, so ICRA 2023, we could see some LLM generative capabilities can generate some code for some new tasks. So everything is now successful. Still, we are ongoing. That is because there are some large linguistic variabilities and also environmental variabilities. So I simply investigate a little bit more about particularly the navigation part. This is a simple categorization of the language-guided navigation. Right, bottom side is probably the most typical one, semantic navigation. Given segmented RGB images and or some map, people are finding a destination on top of some generated low-level motion plan and then perform some navigation. And recent work use more some combined one, that is the visual language navigation, given multimodal input like some images or text, and then predict some final navigation action output. But it still suffers from complex scene or complex instruction. So that there are some additional effort to utilize more structured representation like some graph. So using some topological information, trying to expand the navigation area, particularly the recent one, say plan, is using more abstract information so that makes some scene graph and then exploring multi-room and multi-floor. So everybody is extending its areas. And my lab is also working on scene graph. Here, I'd like to introduce our things. So we are also working on scene graph-based grounding framework. It's basically taking two information, text from speech to text, and also semantic map-based scene graph. And these two information input to the grounding network, we find given some spatial instruction, find destination, and then generate some plan. And here, the scene graph is basically consists of two information, a node and edges. The node is the instance from that scene graph. Edge is the spatial or some semantic relationship. It's quite some compact representation so that compared to the previous some metric map or some semantic map, it's way more some scalable. So last year, our master undergrad student worked on this one really quickly, so that using some YOLO-based detector, we simply made some scene graph, and then message passing-based graph-based neural net, we found latent vector, and then through some pre-trained BERT model, we could ground some target location. And then we input all these framework detection to the grounding, everything to this small size of the quadruped robot with NVIDIA Jetson. And then we could make some robot. So actually this is a Korean model. So if someone use some Android tablet-based command, it's go to some Google Cloud API and then getting text. After then, everything is a standalone. Robot is finding location and also undertaking spatial instruction. So most of things are straightforward, fine. Grounding performance almost 100%. Even there is some spatial instructions, still we could get some very high accuracy. Just the problem is we did the experiment in winter. It was a windy location. So everybody probably has an experience that your command doesn't convert it well, right? If you use a Siri or Alexa. So instruction delivery is actually really challenging. So what we are doing, we are actually using the Google Cloud API. That is because its conversion performance is great. And also it's compatible with many Android devices and also Chrome. Any device can work. Actually, Google Android tablet has some nice filtering hardware so that we could get some many benefits. Just problem is it requires connection, web connection. You cannot load some extreme environment. And also, everybody just assume this is working, but actually it's not working well. So this is the speech text transcript accuracy. The y-axis is the word error rate. Its opposite is actually accuracy. So right bottom, there is some Google, Microsoft, Amazon. They are showing actually 80 to 85% of transcript accuracy. What they mean? At least 1 out of some 10 words will be wrong. So your instruction will be wrong in the end. So it will do some really dangerous task. So the cause of the problem is actually acoustic variability of some human speech or environmental noise. So for example, if we say, I have passed SAT with, it's often transcribed like right side, SA and T. If you are not non-native speaker, we will face some similar problem always. But here we found some interesting thing. Actually, the pronunciation is very similar. So which means similar acoustic property of the word comes from the similar latent embedding in that automatic speech recognition. So in that mean, why don't you use this kind of latent information? Why do you use just text only? So we worked on just 2 weeks we spent, about some 2-3 weeks. So we introduced a new network that is speech scene graph grounding network. Yeah, so as previous model, we are still using the very similar inputs, some scene graph, and also some text. But instead of using Google Cloud API, we are now using standalone program called NVIDIA NeMo. So here we are taking some latent vector that is relevant to the pronunciation, and then input to the district cobalt model. Here the district is a smaller model for your smaller robot. And also the co-mean is trained with the Korean data set. So that we also trained this model using recent technologies, like using some GPT-4. We made many navigation relevant command and also global API. This is basically text-to-speech API, so that we generate many different type of speech, and then we train this work. And this left graph shows 2D projection of the latent embedding from 50 different words. Here, a similar color shows the some word that's starting with similar consonant in Korean. So the word can be, the text can be different. Actually, the pronunciation is very similar. So which means this similar embedding can guide correct grounding. So our observation study shows the use of this latent embedding increased 8% of the accuracy. And also compared to the previous method with some ground truth text, we could increase about 35% of accuracy. We also implemented this onto the quadrant path robot navigation, even though our some operators speech was correct, we could understand, but speech text model generated some wrong text, like there's a red color Korean comment, but still our robot was able to find some correct navigation target. So throughout this process, we could introduce some speech graph-based grounding framework, and also I'd like to say the presence of the similar acoustic properties in embedding can help guide some towards some accurate grounding. So now we are trying to challenge a little bit more, one more challenging problem. So most of natural language grounding work actually working on instance grounding, trying to find some specific object or specific tool. But for example, right side, suppose that we are asking this robot place the dish on top of the table or in front of the bowl. As you can see, this is the continuous space. There are lots of locations you can place, but most of the work really depending on the training data. So basically overfit. So it's not such a scalable, even though there are many possibilities. So here what you want to do is given some expression and also given some multiple expression, we want to robustly ground some target space, not just instance. So for this kind of, we focus on some polar distribution. So polar distribution is basically the joint distribution of the two different things. One is the Gaussian distribution, and another one is the von Mises distribution. This Gaussian distribution is basically used to represent distance, and von Mises distribution used to represent angular distribution. And combining these two, we can represent many different types of space. So for example, this right table comes from the Cartman's work. So they manually associate these two information, some spatial, some expression of some phrase, and specific configuration of the distribution. So for example, given left O, they map this one into left side spreading out distribution, given some near, and this circular distribution. So even though they map them manually, so here, using this distribution and then multiplying, so you throw some linear combination of that, so that we are now trying to represent some various, some space distribution given multiple spatial expression. So our network is very simple. We are using Graphformer. There is some transformer encoder for graph representation, and we input our some text token and also some node token that comes from the scene graph. And also we want to utilize some semantic or spatial relationship between instances. That is input to the network as some edge encoding. That is the basically bias term. After then, through some our linear head layer, it output instance-wise polar distribution and also their importance compared to the input instruction. And then using their some joint distribution, we are grounding a target space. So for example, suppose that someone say, place it to the left side of the coffee cup. In the case, we are getting this left side spreading out distribution of the polar distribution, and also behind, we are getting another, combining these two, we can represent some target distribution. And also, we are not only considering some just instance-wise, we are also considering some the other object, for example, some far from the copy plate, but around napkin cloth. We are also considering these two some spatial expression relation. We are grounding that distribution too. And also, we are not only considering just object, we are also considering kind of some spatial relationship in the scene graph, so that we can ground some the most probable location in this tabletop software setting. So this is some our current student ongoing work, trying to set up some tabletop software placement scenario, given left top instruction, robot is trying to play some software setting. This is basically ongoing, so yeah, just we are showing it's following our instruction. And also, we also tasked that into some our robot, so asking go to the object to the right side of sign, So it's finding the space and also finding the most probable object reaching to that location. So we are working on this space grounding problem, particularly leveraging these polar distributions to represent various space distribution, and also using this distribution and then spatial semantic relationship in the scene graph, we are trying to ground the most probable space. So lastly, we are now, this is a little bit formal task. So given some grounding to task planning and execution. So this is the way before having some LLM-like model. So it's a little bit word work, but it's way more about some outdoor things. So suppose that you are in the outside with this kind of some surveillance robot and asking to this robot to investigate if this better has some any dangerous material or not. So as I mentioned in the beginning, we are providing very simple command only, some check something. It doesn't deliver any detailed information. We don't have some time to write some prompt. So, but robot also has some sensor, but it's hard to observe inside of this better. So basically, it's an extremely challenging problem to the robot. So here, what robot has to do that? It has to investigate or it has to collect additional information. It can be some additional explanation from the user or robot approaching and then investigating, opening or touching. So throughout some collecting knowledge process, after that it has to determine next action. So which means robot needs to collect information over time. Also, it must be able to handle noisy information. So today we have introduced a Bayesian semantic knowledge estimation framework that is basically consists of some three steps: initialization of knowledge about the world, and then updating, and then planning with that. So here the important part is this update model. Given knowledge about the world, particularly some instance, and given some humans declarative instruction, like some this object is full or this object is correct. Given this kind of instruction or actual physical interaction, robot collecting information and update some knowledge about the world model. And if it has some enough information, robot can determine some final action given some imperative instruction, then maybe some explore another world, something like that. But probably this one is every human is doing this. But if robot do, it will take much time to get enough information. So to resolve that, to expedite this update process, we can use common sense knowledge. So now everybody is using some LLM to get some common sense. At the time, we try to use concept net, verbal physics, etc. So for example, in this kind of some large corporate data set, there is information like some on the tabletop, there is some object like some coffee cup, on top of some chair, there is a human. So we are trying to use such kind of common sense knowledge to update. So that, for example, so when we ask the robot to clear the table and also say declarative instruction like the cups are full. So given this additional information and also physical interaction, robot is measuring the status of the object, and with high confidence about the emptiness, robot is throwing away. But sometimes our human instruction can be incorrect. In the case, robot is observing the environment. It's something different. So that in the beginning, confidence is low, but after additional iteration of the observation, finally come up with this cup is empty and then correcting the task. So that throughout this indoor outdoor experiment, we try to show robot can not only following and also updating the knowledge and also correct the command. And lastly, so between the human and robot, some collaboration scenario, there must be many some unexpected situation, like some human is actually helping robot tasks, sometimes interfere. So in the case, we may need some more reactive planning. So for this kind of work, we try to use some LTL basis task and motion planning framework. This LTL was the most convenient tool to express on our ranges and also generate some high level and the low level plan, and then finding some low-level motion plan using dynamically reconfigurable behavior tree, we could make some robot perform complex tasks. And also while doing that, there can be environmental change due to the robot or human or other factor. If there is some small one, we are recovering using this behavior tree. If there's some large change, in that case, there is some replan. But the point of this work is instead of stopping the task, we are just changing, reconfiguring the other part of the subtree so that we could efficiently change the plan while following our command. So this is a simple scenario, just moving left side object to the right side. If someone is just putting some new object, robot is currently having some behavior tree, but suddenly it finds some new object, and this is not immediately reconfigurable. So behind is replanning and then changing the subtree, and then robot is doing it decides to use this one. This is actually some wide shot of some behavior tree to perform manipulation tasks. So for this line of work, I and my colleague, even here, Rohan, and we try to develop some intelligence architecture. This is basically consists of 3 steps. From the perception, we are building a world model, and given our instruction, and then given this world model, generate some task command. And then throughout some high-level mission plan, low-level navigation, motion plan, and also deliberative interaction, we are giving some feedback to the world model so that even there is some change, we are trying to handle. We also deploy many types of robot to the North Carolina in some camp, and then we tested various type of robot, and then we could show robot some interaction capabilities. So we are working on perception, skill learning, and also this natural language-driven some navigation, manipulation skill. And then we believe to develop robotic companion or robotic teammate in future, this kind of technology must work in various diverse environment. So that we are working on. And then this is just summarization. Today I talked about conventional instance grounding, but leveraging some acoustic similarity. And also we are working on space grounding. And I believe these two will gonna contribute to robust instruction deliveries. And also incorporating language guided planning, everybody's working on, but it will enhance some capability of the robotic companion, and we should work on that. Thank you so much.
Okay, there we go, perfect.
Hi, really interesting talk. I was just wondering, your talk got me thinking about the soundscape, exploiting acoustics and speech and so forth, or just at least the sounds around the environment. And I'm wondering if you think about these large pre-trained models, language models, vision models, how might you incorporate the soundscape in such models?
So I never thought about that part, but my just instant answer will be some 2 ways. So anyway, there are many large text speech model, and also NVIDIA Nemo, there is also large language model, and also on other side there is the multimodal LLM thing, but there is currently just associating now some images and text. But I believe in future, probably really near future, it's too fast, everybody's too fast. So that there must be some little more end style of some model, like some speech, multimodal speech vision model, something like that. Probably it will be some one way. Another way is there are so many data sets, probably instead of just using text, we're gonna use speech command and also images or extra. Probably that will be the way we will proceed.
Anyone else? So I guess I can kind of follow up on it real quick. I'm actually really happy that you touched on the speech to text part, the acoustic, because I feel like in natural language these days in robotics, we're all focused on having clean text already, right? And so some of the things that like Jonathan and like even Alice's keynote the other day, these kind of social and cultural nuances that come with even written language. I feel like they're exasperated when you have spoken language, right? Like speaking patterns and dialects and everything. So do you think like, is it just a case of like getting more data to be able to map these like semantically? Or, because I mean, right now, like you point out the speech to text, right? Like they make so many errors. So what do you think ultimately is we can do to improve this more?
So you mean kind of how we can extend this kind of some speech?
Yeah.
Yeah. So here I just focus on the acoustic similarity, but acoustic variabilities can also provide some many information. There is maybe some cultural information or context too. Environmental noise, it is really also very informative source. It may help to grant some right target, but the text cannot easily include such context information, but our some sound thing will be able to complement. So that is probably our some near future work.
Okay, if that's it, then let's thank the speaker again.
Thank you.